Thank you for the introduction. And yeah, let's start the first talk here in the room then. So it's a classical subject in combinatorics to study trees and graphs and such under the effects of symmetry. And today we'll talk a little bit about this in the context of random trees. Namely, we'll study the size of the automorphism of certain classes of random trees. And we'll see that the limiting distribution is log normal. All of this is joint work with Stephan Wagner, who is also here in the room with us today. Yes, so first it should be pointed out that we're talking about rooted trees today. So random rooted trees, that's where we will soon introduce to you. But first, let's talk about automorphisms. And it was actually mentioned in the previous talk. Perhaps we already warmed up to this, but essentially a bijection from the tree itself to itself, a bijection to itself that preserves the edges as well as the roots of the tree. So I drew a picture here before. Let's see if I can switch the camera for you guys. If you can see what I'm pointing at now. Yeah, so essentially we want to have a bijection from this tree to itself, and we would have to map the roots to itself. Then we could either map all the rest of the vertices back to themselves, etc. But there's also another alternative in this particular case. We could kind of split these two vertices on this vertex. This one is here. So in formula, I'm just thinking of this as well, commuting all the branches that look the same, and then we still have an automorphism of the tree. Now, hopefully, heading back to the slides for you guys to zoom as well. So then some unknown fact about automorphism group of a rooted tree is that it satisfies this relationship, this recursion, namely that the size is given by the size of the automorphism groups of each of the branches, because to get an automorphism of the full tree, we need to have an automorphism of each of its branches here as well. And now we're taking the product here over unique branches. So this tree that I drew, it has 3 root branches, but it only has 2 unique root branches because these 2 are the same. And then therefore we need to, for each unique branch, we need to take each of its copies and choose one automorphism for that one, and then we can possibly permute the similar looking ones, like we could permute these branches in the picture I drew. And there, this gives this recursion, which can be useful to us. And it turns out that if we take the logarithm, this turns into something that's called an additive functional of the tree, which has the following form. This is also some sort of recursion then. Now, a bit confusing perhaps, what higher branches are not the unique branches, but the actual root branches of the tree. But to get the additive functional of the full tree, we sum over all of the branches, the value that we get from them individually, and then we add some sort of a toll function, or this is called toll function, some sort of a toll to compensate for what could possibly happen after roots, not just in the branches. So one example here could be that we might be counting the number of vertices of a fixed degree, for example, leaves in a tree. Then we'll need to count the number of vertices in each of the branches. And then we also need to take into account that perhaps the root has the fixed degree that we're studying, and then we need to add something extra. So this would be one example of an additive functional. And in our case, we had, try to switch again. If we were to take the logarithm of the problem studying here, then we would have something looking like this. Like this, I think. So which means that we have, this is our toll function, what happens at the root. And here, well, this doesn't quite look like what we had on the screen because we had unique branches here. And then in my example, what I wrote on the screen, we had the actual branches, but we're multiplying by how many times each unique branch occurs. So we get the same thing if we want to. But the point is that the whole function here is that we essentially will look at all the root branches, and if there are, many of them are will look the same. If they're isomorphic, then this is large, and if they do look different, then this is small. So this is the important part perhaps here. And there's a rich theory on these additive functions for random trees, which we can then use to study this particular one that we're interested in. So this will be useful to us. So then what types of random trees are we studying? Well, I would say that it's the classical one, which will be the Olsson trees, which are then, as you probably know, given by a growth process where we have the root that has a random number of children according to some probability distribution. And then each of its children has children of its own according to the same distribution, but independent of each other. And we are, in particular, we're interested in conditioned Olsson trees, where we condition on the size being n, so fixed size, and then we want them to be critical, meaning that on average each vertex has one child. It is quite typical assumptions to be working with when you're studying Olsson trees. And we'll also be looking at the polytrees, which I mean unlabeled and unordered trees. So these are very similar to Olsson trees in that they have many of the same properties, but they don't fit into this exactly that framework. And something that we'll also need, yes, because it's mentioned one of the theorems that we're applying in our paper, we'll need a site-biased Olsson tree, which is what we get if we condition on the tree going on forever. But if you can think of it as being an infinite spine of special vertices, the red ones in the picture, and then to these vertices we attach the usual Olsson trees that can extend in blue here out from this infinite spine. So the automorphism groups, or the size of the automorphism group, has been studied before. For example, some markers have looked at the limiting distributions of special cases for Olsson trees, or different types of different families of trees. For example, we have people who have looked at binary trees, people looked at labeled trees before, and then a different type of tree, the increasing tree, has also been studied. There has been, well, all of these have obtained then a log normal limiting distribution. And in particular, the first one here is the one that's been most inspiring for our work. So then what are our results? We extend the results from just the special cases mentioned on the last slide to Olsson trees under fairly general assumptions. So we have conditioned Olsson trees with some offspring distribution which is critical, and then we have a somewhat weird / artificial condition on the fifth moment, which is just a consequence of the theorem we apply here. It's probably not best possible, but this is what the theorem requires to be applicable. And then we see that if we take the logarithm of the size of the automorphism group and normalize it properly, we get normal, we get convergence to normal distribution as n goes to infinity. And then, of course, if we have normal distribution for the logarithm of the thing we're studying, then it means we have log normal distribution for the actual thing, that is the actual size of the automorphism group for Olsson trees. And in general, getting the constants, calculating the constants can be quite difficult. We do it for labeled trees in our paper, and due to subsequent developments, we haven't done the calculation, so we can probably do it for Olsson trees with bounded degrees, but in general, it seems to be a bit difficult to do at least singularity analysis to get it, which is the approach we hope to use. Then we also have similar results for polytrees, where we actually have constants, because this is not an entire family of trees, it's just the polytrees. But once again, we have a convergence to a normal distribution for the logarithm for the size of the automorphism group, together with some estimated constants for the mean and the variance. So the arguments we use there, at the first glance, they look quite different, because in one case we apply a known theorem, and in the other one we have to do some more calculations ourselves. But the idea in both of these cases is that we approximate the functionals that turn out to be somewhat difficult to analyze. We approximate them by simpler ones by introducing some sort of cutoff to make things easier for us. So for Galton-Watson trees, this is already done in a theorem for almost local additive functionals, which I will show you soon. So it's like the approximation part is hidden within this theorem, but it's still there. And for polyad trees, we have to do this thing ourselves. So we use generating functions and singularity analysis to study the simpler functionals and get a limiting distribution, and then we can approximate the full thing, the full functional, by using an approximation result to extend the central limit theorem the way we want. So let's start to talk about the case of Galton-Watson trees, where we're applying this new theorem. And then a local additive functional, which should be pointed out, and is the one where if we just look at a local part around the root, we get full information about what the value of the total function is. So we can use some sort of cutoff at, let's say, level m in the tree, and then we can simply figure out the exact value of the total function by doing that. And then an almost local additive functional then is one where doesn't quite hold true, but we can, by cutting off at level m, we get a very good guess of what the value of the total function is. And if we look further down, truncate lower and lower levels of the tree, then we get better and better information. So now this theorem is a bit long, so don't worry about the entire thing. I'll point out the things that were interesting to us. But this theorem is from this paper named Asymptotic theorem for almost local additive three functionals, as one might expect. This is what we're looking at. The first part here is fairly easy to check, so we don't have to worry about that one. And the interesting things for us will mostly be some expected values here. So essentially what these are saying is that if we look, what I said previously is that we can, by looking far enough down in the tree, we get sufficiently good information about the value of the total function, but it's formulated in a bit more complicated way here. And here, this is where the type bias tree shows up, because it's necessarily the proof, and then we have the Olsson trees as well. So there are two conditions here. But essentially what it's saying is that on average, if we cut off at some low enough point in the tree, then we have a very good guess of what the total function is if we look even further down. And it can be interesting to think about what can actually happen when we look further and further down in the tree. So I'm switching to the board again. So what we said was that the total function looks like this, but we want to know if the root branches are isomorphic or not. That's the information that's important to us. So let's say we have two branches almost away from the root like this. Then if we were to look at perhaps some level here, then it's possible that these two trees either look isomorphic or they either look the same or they don't. So if they don't look the same, then when we look even further down, they will still not look the same. We can't be like they can't suddenly switch in that sense. But if they look the same up to this point, then when we look further down, it's possible that they stop looking the same because they might differ at some point further down here. So this means that even though we have some, well, essentially these expectations will be small, if we can just show that it's unlikely that they will look, that the branches will look the same far enough down. We can somehow bound the probabilities by, instead of requiring that they look the same up to some point and then different, we can just say, well, if it's unlikely that they look the same at all, then this will also make the expectations small. So this is the approach we take. So we just found the step we're looking at by something that's simpler. So we look at the probability of trees being isomorphic up to level m. We truncate the trees and look at the probability that they are isomorphic. And then we have to do this for three cases because the way the expectations were built up on the previous slide. But essentially we'll see that we have some sort of exponential decay in terms of how far down in the tree we look, that for two trees to be isomorphic up to that level. These are the Galton-Watson trees. And here we can simplify even further by simply saying that if a Galton-Watson tree belongs to a certain isomorphism class, this certainly will need to have the right number of leaves on every level in the tree. And then we can, this means that we're simply looking at binomial random variables with some fairly simple calculations to check that this actually holds. And then we need some different versions of the same thing. We compare Automorphism trees, truncated versions of those with the size bias tree where we truncate. And then finally, we can extend the results to conditioned Automorphism trees by fairly standard tricks from the study of truncated Automorphism trees. And then when we have these exponential or more or less exponential bounds, then this is what we can use the law of total expectation on the previous slides, and then we do some calculations, and then it turns out that the conditions are all fulfilled, and this gives us the central limit here for what the logarithm the size immediately. So that's quite nice. Then we move on. So now we're looking at the case of the poly trees, where we didn't have the same type of theorem as we had for Automorphism trees. So now we have to do, well, turns out we're doing kind of the same thing in a slightly different way, but we have to do the legwork ourselves. So then we have to introduce some generating functions. We can define a bivariate generating function for the site of the tree, or the site of the automorphism group of the tree, like this. So we have one variable keeping track of the site of the tree and one variable keeping track of the automorphism, site of the automorphism, we call it. And this is all nice because hopefully we can find some sort of functional equation to study this thing and use singularity analysis. But we do have one problem here, and that is that this is not actually analytic for t larger than 0. And to see why, it's enough to consider just the star of invertices. We ignore all other trees, but if we take the star of vertices, then the automorphism group will be n-1 factorial, because we can distribute all of the non-center vertices as we want. And then now we're summing over n, so yes, between for each size, and then we have x to the n. And this is not analytic for any choice of t larger than 0. So this means that this is not analytic where we would need it to be analytic for the singularity analysis to work usually. So that's why we have to use a simpler function to make this work. But we can, even though this is not analytic, we can actually get the variance and the mean by differentiating this formally and then doing singularity analysis still. But it turns out that we can get, even though this is not analytic, we can still get a functional equation for this bivariate generating function. So we use the usual decomposition for poly trees, where we decompose it as a root times some number of branches of each poly tree, each poly tree that we attach to the root. So this is just the usual things that you've probably seen before. But it translates to a functional equation for our bivariate generating function by using the recursion I showed you in the beginning, which was I took logarithm of it and have it on the board, the other one. So this gives us these extra things to compensate for having also the site of automorphism group here. And then we can manipulate this to get iso-looking functional equation that we can actually study. Looking like this. So this looks kind of similar to what you would like the usual functional equation for poly trees, except now we have an extra variable giving track on something more, and then we have this expression C that is somewhat complicated to look at, but it's not too important. It turns out that it's not too difficult to deal with analytically when we need to do so later on. But this is the somewhat horrifying expression for that one. So the problem, like I said, was that this is not actually analytic where we need it to be analytics. We need to do something here to model, let's assume for this anyway. That's when we can introduce a cutoff to get the same thing. And the cutoff we will introduce is in terms of highly symmetric vertices. So like I showed you, the star, for example, is a problem. Because if they can be very too symmetric in some sense, these vertices. So we will, instead of having this call function that we had before, we will have one with an indicator function preventing the contribution of two symmetric things. Now, an indicator function here saying that we only care about the case when multiplicity of some unique tree is less than, let's say, n. So this is by introducing this cutoff, we ignore all the things that were problems to us because they were too symmetric, and then we can actually do the same calculations more or less again, but with this cutoff. To get this thing that looks more or less the same. We have some the function we're using is slightly different because of the cutoff. So therefore I have this less than or equal to n, and then the C thing will also look a bit different. But it turns out this is well behaved, and we can use standard results from singularity analysis to show that we actually have convergence to a normal distribution here. Then we have another fairly long theorem that we don't have to look at the details for, but this one from Remonta's book about random trees, which gives us if some things are satisfied, which I tell you that they are here, then we get convergence of for the logarithm, well, the modified version of the logarithm, the size of the automorphism group. And then finally, we can extend this result from the simpler functionals to the full functionals by using known approximation results. Let us extend. Well, here xn would be the full function we're interested in, and then w and n would be the approximating ones. And then we need to center or we'll normalize these random variables, but then we see that if we have some convergence in distributions for each of the simpler functionals, then we overall essentially only need to check that the variance between when we subtract the full function, the simpler functional from the full functional, that this converges to 0 uniformly in n. And this can actually be done by studying yet another version of the same generating function. Then we can see that by using singularity analysis, the variance actually goes to 0 in the way we want. And this gives us the full result that we wanted. And yes, that's actually everything I wanted to say. Thank you.
You showed convergence in distribution for many types of results. Do you have any sense that, like, you have an almost sure kind of convergence?
No, I haven't thought about that. I'm not sure if Stephan has some input on this.
Almost sure convergence in the sequence. If you have sequence here, you extend the sequence. Would be the tunnel space for all three. This is what you need to sort of try and see
Those of you online, it's hard to hear, but Hossam is asking about almost sure convergence.
This very sense in data growth.
Robin's got a question too.
Yeah. I'm wondering about the general motivation for being able to count the field of Morphism. Does it have to do with wanting to sometimes sum things over Morphism classes with trees or something like that?
I mean, you can also study isomorphism classes, which I've also done to some extent, but I'm not sure. I mean, I just think that it's kind of interesting because it's classical subject to study automorphism groups for usual trees. So also doing it for random trees seems kind of natural in that sense.
Yeah.
Michael.
So thanks for the very nice talk. I really like the slides. It's really nice. It's really nice following you. But I was wondering, like, I guess, like from the functional equation, you can also look like a bounded degree sequences or a fixed degree sequences and so on. Because then, I guess, like you should just, because you have functional decomposition there, you should just look at well, that's degree sequence, so let's look what happens in these kind of trees. Do you know what's going to happen? Or have you looked at that?
No, but I expect, I mean, if you want to look at poetry with fixed degrees or bound degrees, yeah, I expect us to get the same result if we actually do the calculations. I think it looks a lot more messy when you have only like when you try to extract the bounded degrees case, but I think it should work. It should
I
be
don't know
simple.
how complicated your arithmetic and whatever and so on, but in theory, you could just do it.
I think so.
Any questions from our friends online? Okay, so let's thank Christopher one more time.